linear inequalities. A linear inequality in one variable is like a linear equation where the exponents on both the y and the x are ones. So you end up with a straight line graph. Same kind of idea, except the linear inequality in one variable is going to divide the resulting graph into two regions. One region will make the statement true, linear inequality true. The other region will be false. It doesn't satisfy the requirements of the linear inequality. So a boundary line will separate the regions of a graph of a linear inequality in one variable into two regions. Now, if the linear inequality has an equality component, then this boundary line that's separating the graph into two regions is solid. But if there is no equality component, you must put a dashed boundary line. You solve a linear inequality the same way that you solve a linear equation. So you just, while you're solving it, pretend that the linear inequality is simply an equal sign at the end, and you just treat it as an equal sign, keeping in mind that if you multiply or divide an inequality symbol by a negative number, you reverse the direction of the inequality. So you solve the linear inequality. You have to draw a boundary line. You choose a test point, and you shade the region for which the linear inequality is true. For example, y minus x is greater than or equal to negative 2. So I'm going to solve this for y. Add x to both sides. And up with y is greater than or equal to x minus 2. Next, what I'm going to do is I'm going to create a table of ordered pairs so I can make a graph. Well, here we go. So right, so I'm going to calculate some values for y based on these values for x. So when x is 0, y is negative 2. When x is 1, 1 plus negative 2 is 1. And when x is minus 2 plus minus 2 is minus 4. Now I'm going to draw a sketch using these three ordinate pairs that I've just calculated. So I've drawn my axes. Now I'm going to plot some points. When x is 0, y is minus 2. So I'll just say, well, that's a point somewhere there. And when x is 1, y is minus 1. Well, let's put that there. And when x is 2, y is minus 4. Well, let's say there's a point down there. So now I'm going to draw my boundary line. Now, the rule here, remember, for the boundary line, if the linear inequality includes an equality operator, then the boundary line is solid. Well, what case do we have here? We've got an equality operator. You see that right there? So the inequality is y is greater than or equal to x minus 2. So I'm going to have a solid boundary line. So now I've indicated my boundary line. The next step in the process is to choose a test point. Well, almost always the best test point to choose is the origin where the x and the y axes cross, 0, 0. So there's my test point. I'm going to indicate it on the graph right here. And what I'm going to do is I'm just going to write down that information. 0, 0. And now I'm going to test to see if that point actually makes the inequality true. Well, the inequality itself is y is greater than or equal to x minus 2. Well, I'm going to take my values for x and y, the values of my test point, and put them in the inequality. So when I choose the origin as my test point, the value for y is 0. 0 is greater than or equal to, well, the value for x is also 0 minus 2. Well, this means that since 0 is greater than or equal to 0 minus 2, well, this reduces to 0 is greater than or equal to minus 2, which is true. This is a true statement. That means that the point 0, 0 is actually on the side of the boundary that makes the inequality true. So I'm going to actually shade that in like so. So to recap, the test point 0, 0, when fed into the original inequality, results in a true condition, which means that the test point lies on a side of the boundary line, which makes the inequality true. So that's the side of the boundary line, which is shaded. So everything on the shaded side of the boundary line, including values on the boundary line, make the inequality true. Well, let me just explain that last point. But what about a value that's on the boundary line? Well, let's take a look at the ordered pairs. The ordered pairs were used to generate the boundary line. So I'm just going to take a look at the first ordered pair, 0 and minus 2. Let's just do the same calculation. Well, I'm going to be using the inequality y is greater than or equal to x minus 2. Well, with the first ordinate pair, x is 0 and y is minus 2. So I'm going to feed those numbers into the inequality. So y is minus 2 greater than or equal to, well, if x is 0, 0 minus 2. So this reduces to minus 2 greater than or equal to minus 2. Notice that the inequality symbol is greater than or equal to, which means that you can have equality and still have a true statement. Well, in this case, minus 2 equals minus 2. So once again, this is true. So the boundary line itself also satisfies the inequality, and that's why it has a solid line. I'm going to do another example now with the inequality 3x plus 2y is greater than or equal to 6. Let's take a look at this. So I'm going to solve this inequality for y. I'm going to add negative 3x to both sides of the inequalities. And now what results is 2y is greater than or equal to minus 3x plus 6. Now I'm going to divide both sides by 2. Anything divided by itself is 1. I'm not dividing by a negative number, so I do not reverse the direction of the inequality sign. I can divide 6 by 2 to give me 3, so I'm going to reduce that fraction, 6 halves, to 3. So there is my inequality. Now what I'm going to do is graph that inequality. So now I'm going to generate some values for y. I chose 3 values for x. Notice that I'm going up in increments of 2 because the denominator of the term, including the variable, is a 2. So when x is 0, well, y equals 3. When x is 2, minus 3 times 2 is minus 6. Minus 6 divided by 2 is minus 3. Minus 3 plus 3 is 0. When x is minus 2 times minus 3 is plus 6. 6 divided by 2 is 3. 3 plus 3 is 6. Now I will graph these points. Plotting the points when x is 0, y is 3. I don't know, we'll just call that goes there. When x is 2, y is 0. And when x is minus 2, y is 6. So our boundary line looks something like that. It's a straight line. Now I'm going to draw a solid boundary line because our inequality symbol is greater than or equal to, so it's a solid line. Now that I've got a graph of the boundary line, I'm going to include a test point. I'm going to use the test point 0, 0 and see if that test point makes the inequality true or not. Let's try that out. Here is the inequality. Y is greater than or equal to minus 3x over 2 plus 3. All right, so my test point is 0, 0. So when that means the value for y is 0 minus 3 over 2 times 0 plus 3. Well, let's just see what happens with the test. Anything times 0 is 0, so that becomes 0 plus 3. So minus 3 times 0 is 0, divided by 2 is 0. And so now 0 is greater than or equal to 3. Well, that is false. That is not true. That means that the test point indicates that the side of the boundary line containing the test point does not satisfy the inequality, does not make it true, which means the other side must make the inequality true. So I'm going to shade that. There. And that means that any point on the side of the inequality, or on the side of the boundary line that I have shaded, will make the inequality true. Also, any point on the boundary line will also make the inequality true. So now I'm going to solve another linear inequality. Notice that with this linear inequality, the inequality sign does not have an equality component. So I'm going to solve this inequality for y. Here we go. Two x plus y is greater than 5. Subtract 2x from both sides of the inequality, and then what I have is y is greater than minus 2x plus 5. Next, I'm going to make a table of ordered pairs. 0, 2, and minus 2. So when x is 0, I'm finding the boundary line here. When x is 0, 2 times 0 minus 2 times 0 is 0, plus 5 is 5. When x is 2, minus 2 times 2 is minus 4. Minus 4 plus 5 is 1. When x is negative 2 times negative 2 is plus 4. 4 plus 5 is 9. So I have some points that I can plot to determine my boundary line. What I need to be careful of here is I am dealing with an equality sign that has no, an inequality sign that has no equality component. This is simply a straight up inequality sign. So my boundary line will be a dashed line, and no point on the boundary line will actually satisfy the condition of the inequality. Okay, now I'm going to make a graph. All right, I've plotted my ordinate pairs, and now I'm actually going to draw a dashed line from a boundary line. Here we go. Arrowheads and the ends of my boundary line, because the boundary line actually goes on for infinity in both directions. And now I'm going to locate a test point. at the origin, 0, 0, and I'm going to test whether the inequality is true using the test point. So here we go. Well, the inequality is y is greater than negative 2x plus 5. Now I'm going to put in the values of my test point. Y is 0 minus 2 times x is 0 plus 5. Well, anything times 0 is 0, so this becomes 0 plus 5. 0 is greater than 5. Well, that's false. That means the test point does not lie on a side of the boundary line which satisfies the inequality, which means the inequality must be satisfied by any point on the other side of the boundary line, the side of the boundary line not the side of the boundary line not containing the point 0, 0. So now I'm going to indicate that by shading in the portion of the graph on the side of the boundary line that does not contain the point 0, 0. And I'm going to be careful to not allow my shading to actually touch the boundary line, because the boundary line, once again, does not satisfy the inequality. So there. So that is the graph of the inequality 2x plus y greater than 5. Well, I'm going to solve another inequality. In this case, 5x plus 3y is less than 15. Here we go. So I'm going to solve this inequality for y. This is how I can find my boundary line. So I'm going to add the additive inverse of 5x to both sides minus 5x. This means I have 3y is less than minus 5x plus 15. Now what I need to do is isolate y. So divide both sides by 3. Anything divided by is a 1. So I have y is less than minus 5x over 3 plus 15 thirds, which reduces to y is less than minus 5x over 3 plus 5. All right, I'm going to make a table of ordered pairs and make a graph to determine the boundary line. So I will do my ordered pair table, just right here. So I'm going to use 0 for x, and because the denominator of the term containing the variable goes up, or has a 3 in it, I'm going to go up and down in increments of 3. So anything times 0 is 0, so minus 5 times 0 divided by 3 is 0. But then plus 5 gives me a value of 5 for y. Next, I'm going to go minus 5 times 3 is minus 15. Minus 15 divided by 3 is minus 5. Minus 5 plus 5 is 0. Finally, when x is minus 3, minus 5 times minus 3 is plus 15. Plus 15 divided by 3 is 5. 5 plus 5 is 10. Again, this boundary line will have a negative slope because of the negative sign in front of the term containing the variable. Now I'm going to make a graph of the boundary line. So I'm going to plot my points. When x is 0, y is 5. Fine, I will say it's there. When x is 3, y is 0. We'll say it's there. And minus 3 and 10. All right, once again, this inequality does not have an equality component. So my boundary line will be a dashed line. Here we go. We'll draw the dashed line. All right, I'm going to choose a test point. I'm going to choose 0, 0 as my test point. I'm going to try to determine here whether the test point satisfies the inequality or not. So here we go. The inequality itself is y is less than so I'm going to substitute in the values of 0, 0 for y and x. And in this case, because 0 is less than 5, the test point does lie on the side of the boundary line, which makes the inequality true. So I'm going to indicate that by shading in the side of the graph where the inequality is true. Being careful not to touch the boundary line, because the boundary line itself does not make the inequality true, because there is no equality component to this inequality.